Hello everyone, welcome to another video. Today we'll be picking up where we left off in the last video on dark matter, as today's discussion pertains to dark energy and how it is a dominating force in terms of the future of our expanding universe. So what is dark energy? A mysterious substance composing roughly 68% of the entire universe. Dark energy is thought to be an anti-gravity force in some sense, providing a negative pressure throughout the cosmos, stretching and expanding the fabric of space-time. First discovered in 1998 when astronomers were observing Type 1a supernovae, which is a special type of cosmological event that always has the same brightness when it occurs. This phenomenon is called a standard candle, in which observing this event and taking notes of the apparent brightness of the event tells us how far away Type 1a supernovae are, giving us great insight on distances and changes in sizes within our universe. In utilizing standard candles and observing that Type 1a supernovae appeared to be fainter than expected by previous models of an expanding yet slowing universe, this told astronomers that the universe must be going through a phase of accelerated cosmic expansion. In order for these standard candles to appear fainter, the fabric of spacetime must be expanding the space in between these objects faster than original models predicted. This brings us back to the concept of dark energy being behind this accelerating cosmic expansion, which although we cannot observe through direct detection so far, we know the substance exists due to its effects on observable objects that dark energy surrounds throughout the cosmos. However, one key distinction to keep note of is that although dark matter and dark energy share similar names to one another, due to the two unknown substances both being invisible to all attempts of detection thus far, these similar names are all dark matter and dark energy seem to have in common. For example, the effects of dark matter take place on smaller scales, which are less than 10 megaparsecs, in contrast to the effects of dark energy taking place on scales larger than 1000 megaparsecs. This is why you don't see your phone or computer rapidly accelerating away from you as you watch this video, despite dark energy composing the majority of our universe. Even on the smallest of scales, mass and its associated gravity still beat this expansion force. While dark matter clumps up and has local gravitational effects on the visible matter in our universe, dark energy does not. Dark energy, in fact, is evenly distributed throughout the cosmos, both spatially and temporally, meaning its expansion effect is not diluted as changes persist throughout our universe over time. Therefore, instead of having local impacts on the universe, this repulsive force has a global effect on the universe as a whole. This phenomenon also plays a role in why large cosmological objects, such as galaxies, galactic clusters, and superclusters, aren't ripped apart by the accelerating expansion of our universe. While on the topic of how cosmic expansion works, one thing we do know about dark energy is that in going along with the idea of dark energy only having effects on the largest of scales, the greater the distance that separates cosmic objects in outer space, the more rapidly those objects will accelerate away from each other. One way to imagine this is by drawing 3 dots on a deflated balloon, with 2 close together and the third farther apart. In this sense, dark energy is the breath being blown into the inflating balloon, while the 3 dots are large cosmological objects in outer space. As the balloon inflates, you'll see all 3 dots moving away from each other. However, the third dot that was placed farther away initially can be observed to move away from the other dots more rapidly. In essence, the more empty space present in our universe, the more cosmic expansion there is. This in part contributes to why the cosmos is not just expanding, but doing so at an accelerating rate, since the act of cosmic expansion creates more empty space, which in turn causes more cosmic expansion, and so on and so forth, over and over again. Recognizing this vicious cycle of seemingly endless cosmic expansion as time continues to progress helps in understanding how dark energy gained the upper hand in the cosmological tug-of-war with dark matter. For the early course of our universe's history, the dominant force of the cosmos was dark matter and all other forms of matter containing mass that subsequently form gravitational fields associated with said masses. With a slowing expansion rate of the universe, large cosmological objects were able to form, which in today's accelerating cosmic expansion would be extremely difficult and rare to form. This slowing expansion, changing into an accelerating expansion, is thought to have occurred when the universe was roughly 7 billion years old. Scientists estimate that the current expansion rate of the universe due to dark energy is 67.15 plus or minus 1.2 kilometers per second per megaparsec, in which it is thought that galaxies are getting 0.007% farther away from each other every 1 million years. One final point to note about dark energy, before we move on to potential candidates for dark energy, is that with the notion of farther away objects in outer space accelerating more rapidly away from one another with cosmic expansion, you may be wondering what happens when approaching the speed of light. One of the most interesting properties of dark energy is that the expansion of our universe is not bound to the cosmological speed limit set by Einstein's theory of special relativity of 300,000 kilometers per second, otherwise known as the speed of light. This is because, although objects within space cannot travel faster than light, this cosmological speed limit does not apply to the effects of changes to space itself, meaning there is no maximum speed for the expansion of the cosmos. We've seen this play out in some of the oldest galaxies ever discovered, such as in the case of galaxy GN-Z11. Under the false notion that in a 13.8 billion year old universe, we'd expect there to be nothing farther than 13.8 billion light years away. However, galaxy GN-Z11 is estimated to be 32 billion light years away, moving away from us at an estimated speed of 687,000 kilometers per second, which is over twice the speed of light. This confirms that the expansion of space itself is not confined to expanding at such a speed limit. So what actually is dark energy? Our first candidate is called the cosmological constant. Often represented by the Greek letter lambda, the cosmological constant was first introduced by Albert Einstein in his theory of gravity when he needed an anti-gravity force to explain what he thought at the time was a completely static universe with no expansion whatsoever. He would later throw out this fudge factor in the 1930s when Edwin Hubble proved that the universe was not static, but actually expanding. With Einstein's greatest blunder discarded from explaining cosmic expansion, it wouldn't be until many years later when this cosmological constant began to gain significant attention. This revival of the cosmological constant stems from the discovery that the universe was not only expanding, but also accelerating in its expansion rate. The cosmological constant explains the idea that space itself contains vacuum energy, which in the absence of matter allows more space to emerge from this empty space. Since this vacuum energy is thought to be a property of space itself, the emergence of more space also means that this newly emerged space has new vacuum energy of its own. In doing so, this tells us that vacuum energy can never be diluted, causing not only cosmic expansion, but over time accelerating cosmic expansion. The most peculiar thing about Einstein's long-discarded cosmological constant, though, is that for some reason, the cosmological constant has exactly the right value to cause the observed acceleration of our universe. This intrigued scientists to revisit the cosmological constant, which in the quantum theory of matter suggests empty space is actually full of temporary virtual particles that instantaneously pop in and out of existence. However, when physicists tried to calculate how much energy this would give empty space, the number was 10 to the power of 120 times larger than expected, leaving physicists puzzled as to where their theorized estimate went so horribly wrong. Our next candidate for dark energy is called quintessence, a hypothetical energy fluid thought to fill the emptiness of outer space. Named after the fifth element of the Greek philosophers, quintessence is a low-energy quantum field filled with tachyons, which are hypothetical particles that supposedly travel faster than the speed of light, meaning these particles travel backwards in time. Unlike the cosmological constant, which is specifically vacuum energy, quintessence is thought to be a dynamic, spatially dependent form of energy bound to change over time. Where the cosmological constant has a fixed energy density of W equals -1, quintessence calls for an energy density for empty space that is capable of changing over time. Using the equation of state pressure equals energy density times density, if quintessence is in fact dark energy, it is hypothesized that the energy density W would need to undergo a transition to less than W equals -1/3 in order to initiate the accelerating cosmic expansion we observe the cosmos to be going through today. The next idea for what dark energy could be takes a more skeptical approach, as there is the possibility that Einstein's theory of gravity is wrong, and that a new theory of gravity is needed to account for dark energy and our universe's accelerating expansion. Einstein's theory of gravity and general relativity currently states that gravity is the curvature of the fabric of spacetime, in which this curvature on the fabric of spacetime is caused by all objects with mass and/or energy. Although possible, the chances of Einstein's theory of gravity being wrong are very, very slim, as general relativity has not failed a single application throughout the universe so far. In trying to develop a new theory of gravity, one would not only have to accurately account for how cosmic expansion behaves in the various manners it has throughout the past 13.8 billion years, but also redo all of general relativity's accurate work in correctly describing how all normal matter behaves, such as the formation and evolution of galaxies. Therefore, to say such a task would be extremely difficult is an understatement, meaning the mystery of dark energy continues. Our last candidate behind dark energy and cosmic expansion is the weakest argument and most speculative of the candidates we've covered so far. Some scientists believe that in addition to the four fundamental forces of the strong nuclear force, electromagnetism, the weak nuclear force, and gravity, that there could potentially be a fifth fundamental force responsible for dark energy. This is derived from the idea that although the Standard Model is a great triumph in scientific understanding in terms of all it does for physics, it is still at best incomplete. Although there is room within the Standard Model for such a fifth fundamental force to exist, no evidence has been found thus far. Leaving this idea to be pure speculation, this idea is much less likely to end up being our answer behind dark energy in comparison to the other ideas we've discussed throughout this video. Alas, we are left yet again with many possibilities for what another vitally important mystery may be, leaving the door open for endless theories and experiments to try and fill the void dark energy and dark matter leave in our scientific understanding of the cosmos. Only time will tell what truly makes up 95% of our universe. But until then, we must continue our journey in learning more about the universe. Stay tuned for the final video in the Origins of the Cosmos series, where we'll tie in what we do know so far about dark energy and dark matter in an attempt to map out the future ahead for our universe. Thank you all for watching. If you enjoyed this video, please consider liking and hitting that subscribe button with the notification bell on. To learn more about dark energy, see the links to the research I used for this video in the description. If you haven't already, make sure to check out part 1, where we explored more on dark matter. If there are other ideas you'd like to see covered in a future video, please leave it in the comments below. Have a great day, everyone, and remember to stay curious.